A good day to you all. As Group 3, we'll be presenting with reference to case studies, outline the importance of machine learning in the prediction of ground motions and measures that can be implemented in areas with sparse geophysical data sets. Firstly, we'll define what machine learning is. So machine learning is the use and the development of computer systems that are able to learn and adapt without following any instructions by using algorithms and statistical models to analyze and draw interferences from patterns in data. Also, it is a branch of artificial intelligence and computer science, which focuses on the use of data and algorithms to initiate the way in which human beings learn, gradually improving its accuracy. Also, machine learning has played a significant role in the prediction of ground motions. That's in seismology and earthquake engineering. One of the challenges in predicting those ground motions is the complex and uncertain nature of the underlying physical processes. So this challenge is compounded in areas with sparse geophysical datasets where traditional methods may also be inadequate due to lack of data. Then the approach of addressing this challenge is to use machine learning algorithms to extract patterns and also relationships from the available data. Machine learning can also be used to identify the complex relationships between input variables that include earthquake magnitude, distance from the epicenter, and the geological features, and also ground motion parameters such as peak ground acceleration, peak ground velocity, and displacement. Then those relationships can then be used to predict ground motions in areas where the data is sparse. Also, machine learning has played a crucial role in the prediction of ground motions, also in areas with sparse physical data sets. Then there is need of accurate predictions of ground motions, as they are critical in the assessment of seismic hazards, planning, designing of robust infrastructure. And also there is need to implement effective early warning systems. So there are also case studies that have indicated the importance of machine learning in the prediction of ground motions. So basically there are two case studies. The first case study that was performed in 2018 by Zhuang and his colleagues, they used machine learning algorithms to predict motions in the Himalayan regions, and this area is characterized by sparse and heterogeneous data. And results from the study were found out that machine learning algorithms were able to predict accurately the ground motions even in areas where the data is limited. Also in 2019, the second case study, the study was performed by Wang and his colleagues, and this was done in the Taiwan regions, and machine learning was also used to predict ground motions. And also, machine learning was also able to predict high ground motions with higher accuracy than traditional empirical models. in the areas with limited data. That's under the first technique, that's the deep learning for ground motion prediction. And researchers have developed deep learning techniques, namely the convolutional neural network and the long short-term memory. So these techniques are able to predict strong ground motions from earthquake scenarios. Also, they capture highly nonlinear features of ground motions, which enable these models to predict accurate features. And these features, like I had said earlier on, their peak ground velocity, peak ground acceleration, and ground displacements. Then the second model after deep learning for ground motion prediction is earthquake early warning systems. So machine learning has been instrumental in early warning systems for earthquake predictions. In our case study, that's in California in the year 2017, where researchers combined both earthquake catalogs and ground motion recordings from multiple sources to predict seismic events with high accuracy using the machine learning models. Then there are also measures taken into consideration that are also implemented in areas with sparse data sets. So the first measure is to conduct geophysical surveys. So basically the geophysical surveys involved measuring of the physical properties of the subsurface using various techniques such as seismic, magnetic, gravity, and electrical methods. These surveys also provide information about the subsurface geology and help identify the potential mineral or hydrocarbon deposits. The data collected from the surveys can also be used to create 3D models of the subsurface and are also used for exploration and resource management. The second measure is the collection and the analyzing of geological samples in areas with sparse geophysical data sets. Collecting geological samples provides valuable information about the subsurface. Samples can be collected from the surface outcrops or through drilling. The samples can be analyzed to determine the composition, the structure, and the age of rocks, which can provide insights into the subsurface geology. Then the third measure is the use of remote sensing techniques. So remote sensing techniques such as satellite imagery and aerial photography can provide valuable information about the surface features of a particular area. The information can be used to identify the potential geological structures such as faults and folds, which provide clues about the subsurface geology. Then the use of collaborating with other neighboring regions. That's the fourth measure. Then if regions neighbor among themselves, they have more extensive and geological data sets, and this can provide valuable information about the subsurface. Data sharing agreements can help and also provide a more complete picture of the subsurface geology. Then the fifth measure includes drilling, and exploratory drilling involves drilling test holes to collect subsurface data. Then this information collected also provides direct information about the subsurface geology, and also the data collected can be used in these models and improve the accuracy of the estimates.